A very good afternoon to you all. Uh, I'm Vandita Srivastava from IIRS Dehradun, and you are attending this program on Geographical Information Science in the IRS Outreach program. Welcome back to this session on spatial data analysis. Yesterday, we discussed a couple of things. We had an introduction to spatial data analysis and we discussed some operations. I'll just quickly browse through them and then we will start today's session. We were talking, this was the coverage and we had discussed about the introduction part. Then we talked about retrieval and selection operations, measurement, and today we'll be discussing on classification overlay operations and also a quick overview of the neighborhood and connectivity operations. So, we talked about these concepts of spatial data analysis, the spatial and non-spatial queries, classification of various functions, and steps involved in a project. I will also show you an example of site suitability analysis. Then we discussed about the retrieval and selection operations. So we were on this agenda item 2. We had completed up to here, and now today we will discuss this. So, arithmetic relational operations, logical operations, just to give you a quick overview, and then retrieval using pixel information window, interactive, and selection by attribute and spatial relationships. So now I'll talk about the classification and reclassification operations in GIS, which is different from that in image processing. So, we will talk about the M2N classification, control versus automatic classification, and also equal interval versus equal frequency classification in the automatic one. So, before even we start the talking about various types of classification methods, let us first understand what is classification. Although it is a very generic concept, we all understand, we all know what is classification. We can express it in this form that it involves selection and presentation of a selected layer or selected data set based upon some specific attribute. So we want to categorize our data based upon certain specific attributes, that is classification. It involves looking at an attribute or a series of attributes. We can have first primary attribute, then secondary attribute. Like that also we can do classification for a single data layer, or even, so usually it is performed on one layer at a time. So it is a single layer operation. And then we classify the data based upon the ranges of the values that are present for that particular attribute in that layer. Okay. And why do we want to do this? Because sometimes we don't want extra details to be present in our layer. We want specific information. So we would like to remove the unnecessary details that are present in the data set. Okay, and this removal of unnecessary details will actually help us in identifying the useful patterns. So we would be able to focus upon those useful patterns. If you recall my class on the introduction to GIS, we were showing a table and then immediately we showed a map. So you could reveal a lot of patterns of data just by displaying. So you can imagine that if we perform further the classification and reclassification, then we can reveal even more patterns which were hidden in the previous data. But the moment you classify it, you can reveal. So there are many ways of actually extracting the information from the data set. So this is one of the methods. Fine. And then of course, we can reduce, or sometimes we can even increase the number of classes if we are talking about disaggregation. But in the aggregation, we are reducing the number of classes. So eliminating the details. If the input data set itself is the result of classification, then we call it as reclassification. If we are classifying the data which is not yet classified, we call it as classification. If it is already classified data and we are further performing reclassification based upon a different classification scheme, then we call it as reclassification. And we classify the data and reclassify the data in different systems for different purposes, for different specific applications. I will show you supporting figures to this statement in my subsequent slides. So, and assign codes based upon specific attributes. So we can even do reassignment of the new codes to those attributes based upon our purpose of study. So we have these classification and reclassification, and post processing is also sometimes required when we perform classification and reclassification. And the classification methods, as I said, are of two types. The user controlled classification, wherein the classification table is decided by the user, while in case of automatic classification, the user only tells the number of classes in the input and the output, and the algorithm decides the classification table. So there are two methods, equal interval and equal frequency classification. This is nothing new. Those who have studied up to 10th class, you would have studied the equal frequency and equal interval classification in your statistics, very basic statistics classes. Maybe 10th or 12th you would have studied this. So let us discuss now the three types of classifications. 1 to 1. Here 1 does not mean literally 1. It means the equal number of classes in the input as well as in the output. So if I am having 5 classes in the input, I am having the same number of classes in the output as well. Only the classification scheme will be varying here in this case. Then you have many to one, wherein we have more to less. That is, more number of classes in the input to less number of classes in the output. And then we have one to many, the reverse of the second situation. So let us see some examples of these. So this is just an example wherein household income has been classified into 5 categories: low, below average, average, above average and high. So from low to high it is varying. So these are 5 classes that are present, and you could also classify soil types, classified in based upon soil suitability for some specific agricultural purposes. You could also reclassify a slope map into high, moderate and low slopes. If you require more number of classes, you could again do the same thing: the high, the above average, average, below average, low altitude, or height or slope. So you can make your own classification scheme based upon your purpose of study. And you can also classify an elevation map with the interval of 50 meters or so. So what is the basic purpose of your study? That will decide what will be the classification scheme. Now let us see some examples of these. So here is an example of the attribute map wherein land use is shown here and these 5 categories are shown. Now if I want to classify this based upon another column, which is city block ID. So each block has got a unique ID. If now I want to show or classify this map, because I am, let's say, interested in making an analysis which is city block wise. So every block is given one ID and I want to do all my analysis based upon this city blocks. So I would like to have a map that represents the IDs. So this will also be done using classification, and we can simply use the city ID as the classifying attribute. So this is what we will choose as a classifying attribute, and you get this as an outcome. Now this is an example of less number of classes to more number of classes. Each city block ID here is a class. So this is an example of one to many classification. Similarly, if you have more number of classes in the input and less number of classes in the output, in this example geological map which was classified into 7 classes is now classified based upon lithology only into 3 classes, main lithological classes: metamorphic, igneous and sedimentary rocks. So now you are getting from more number of classes to less number of classes. Sometimes this kind of simplification is required in order to have a better idea. You can actually see that you will see a different pattern of distribution of these classes as compared to this input map. So this is required sometimes, and you can perform it in this way. And this is equal one-to-one classification, wherein the income groups which were categorized from high to low in 5 categories, the same low and high categories are there, but their definition has changed. If you see here the classification scheme here as well as here, it is neither equal frequency or equal interval classification. You have 0 to 50, 50 to 100. So up to here 50,000 is the interval, but from here to here it is 25,000 is the interval, and then all other values more than 150,000 have been clubbed into one. So this is one classification scheme. In the output also there are 5 classes, but here the focus is on the low income group. So you can see the earlier classes are of 25,000 interval up to 70, actually up to 100,000, and then more than 100,000 has been grouped. So where you would use this kind of classification change, wherein you specify what is your focus, which income group is your focus. Based upon that you can change the classification scheme. So this was an example of one-to-one classification. And then you can also classify, this is the reverse of one to many. Here we are making many to one, but again using the attribute map. So this is an example from IIRS software, which was using the attribute table, column in the attribute table in order to make this kind of map. You can also do it in ArcGIS and other softwares using various other commands. The commands may vary, but the concepts remain the same. So you can always do what you can do in one software, you can always do it in another software most of the times. Now this is another way. This is again example from IIRS software, but you can do similar kind of calculations in Spatial Analyst in the Raster calculator. So here also we are doing classification from 3 classes to 2 classes based upon infiltration. So here you had soil table, the soil classes are present, but from that now you are classifying based upon infiltration. So it is an example of many to one classification. You can also classify with the help of this kind of conditional if statements. It is called as this is how it is expressed. Output map is assigned equal to if and only if this condition is satisfied. Then you execute the then expression, this expression in this bracket, in this phrase, otherwise execute this expression. So you can say if infiltration is equal to 30, then give me 30, else, or let's say if the soil type is 1 or soil type is 2, then give me infiltration as 30, else give infiltration value as 25, and this output map you can put as infilt. So that is how you can get this kind of map. So you can also do classification using the if statement, conditional if statement it is called. And you can also, so this is the expression that I was talking about. Infiltration is if and only if soils is 2 or soils is 1, then give me 30, else give me 25. You can also classify, instead of making 30 and 25, you could say 3 and 0. So make if this is Redzina, because this is a shorter statement. So if you see here, your statement is longer, this one is shorter. So depending upon the distribution of the data sets or the data values, you can design your shorter statements. The shorter you design, the better it is, because then the statement is simple and you can understand it. Okay, and this is another way of getting the classified map using the column in the table in the map. So this kind of statement structuring is done in IIRS. This is not present in ArcGIS, but you can also explore other software if it is present. But if not this way, then there will be some other way, but you can still get this kind of map and using some other operation. Then this is an example of conditional if statement which is nested. So if inside a if, there is one if statement inside another if statement. Then there is this format already I showed you, the input map dot the table and dot the column. Actually the column name, the new map name is equal to the the table name dot the column name. That is the format. And you can also this is again IIRS concept, wherein you use domain concept to define the classes, and you just simply use the domain instead of the attribute. That particular domain will be used to categorize. So this domain is nothing but the definition of the classes. Then there is a classify command. This is a command prompt version of the command, of the same command, something like this, which is using the classify button and then classify command, and then using the map name and the column name inside the map to get this output value. So various ways are there to make the classification. Now as I said that once you perform classification, you may have to do some post processing. If you look here, if we merge those household income classes like this with one with the classification scheme given, this kind of you know resulting will be there, wherein the earlier 5 polygons which were different classes now are a part of the same class. So here you, because now it is part of the same class, you would like to dissolve these. So you may need to dissolve these polygons into one. So after dissolving, this is the outcome, that is how it will look like. Similarly, these ones have to be dissolved. So you can see that they have been dissolved here. So even these ones have to be dissolved. It has become all one class. Likewise at these places it has become all one class. Okay. So that way one has to do post processing after classification to get more appealing maps, and having a direct one-to-one correspondence with the table as well. So if you don't do this dissolving, then you will have more number of rows records in the table, but the classes are less. So it does not appear to be a very appealing outcome visualization wise. Therefore you should do this kind of dissolving so that there is a one-to-one correspondence and there is a clarity in the data set. This dissolving could be called merging or dissolving. So that depends upon how the software is written, what they are calling. So you need to read each and every command what it represents so that you can make best use of it. Okay. Now user control classification, I told that the user indicates the classification attributes and specifies the classification method. The number of output classes and the classification table, all of this is given by the user, like this one. So all of these planned residential and unplanned residential are all merged into the output class residential. Similarly, industry commercial are merged into commercial, the institutional transport and recreational are merged into public. So this is the new classification scheme, this is the old classification scheme. But here the classification scheme, the number of output classes, the input classes, everything is decided by the user. But in case of automatic classification, the output number of classes only is given by the user. The classification scheme is decided by the algorithm. I will show you how. So in this user control classification, like this is a elevation, and the values are from here to here, from 94.738 to 3070.291. Now this number of classes are classified into only 5 classes. So these are given as values 1 to 5 and then no data. Okay. So now you see here only 5 classes. You could also put less number of classes, and the top and the bottom values you could put as no data. So when you do this, you see the highest and the lowest elevations as black, as no data, but only the in between classes as class number 1, 2 and 3. This you may like to do based upon your requirement, that you are not interested in the low elevation or the highest elevations, you are interested only medium elevations. Maybe you may require this for the purpose of plantation or to study vegetation, wherein you are not interested in these elevations. So you may require to classify like this. Okay, that is an example of user control classification, wherein you can manipulate the classification scheme based upon your purpose. But automatic classification has got a fixed scheme. So it is so as I said, the user specifies the number of output classes. The classes in the input is already given, so we need not talk about the input number of classes, but output classes are given by the user. The computer decides, the algorithm decides the class breakpoints, that is the class interval, where to break this data. This happens usually for the numerical data set. So there are two schemes, equal interval and equal frequency. In case of equal interval, the class interval is calculated like this: the maximum value minus the minimum value divided by the number of data points. And equal frequency classification, that is also called as quantile classification, uh, basically the purpose here is to maintain the equal number of data points in each class, in the each output class. So it maintains equal or nearly equal, because sometimes maintaining equal number of features may not be possible. So nearly equal is used. So equal or nearly equal number of features in each category in the output. So let us say this is the grid, and if I wish to make a classification using equal interval into 5 classes. Now you see we have 10 number of points, 10 number of features here. So here this becomes 10 minus 0, or 10 minus 1 divided by n. So we get roughly 2 classes into 1. Okay, so 5, because we have to have 5 classes in the output. So 1 and 2 are merged as 1, 3 and 4 are merged, 3 and 4 here are merged as 2, and 5 and 6 are merged as 3, and then this 8 is merged as 4, and 9 and 10, 7 and 8, 7 is not present here, so only 8 is there, and then 9 and 10 are merged as 5. So you see here 5. So this is 4, 4, 4, and this is 5, right? So this is how equal interval classification works. Now equal frequency classification. So this is the output assignment table, the original classes, and the now number of pixels in each output class is not equal. You see the last class has got only 2 pixels. These have 3, these have 9. The first and second, the first new class has got 9 pixels. So the distribution of number of pixels is not uniform. Okay, that is why you may like to, if you want to see the equal representation from each data class, input class, then you would like to have a equal frequency classification, and for that you would need to basically divide the number of data points by the output classes. So if here we have 5 by 5, that is 25 divided by 5 classes. So we need to see that at least 5, roughly 5 data points come into each class. For doing that, your classification table will be something like that, because we have in the first class itself we have 6 points. We will not touch upon this class. So this class remains the same. Now 2 and 3 are merged together, because the second class has got 1, 2 and 3 pixels or data values, and the third one has got 2. So 3 plus 2 becomes 5. So we have roughly better representation of each class in this equal frequency interval, equal frequency classification than in equal interval classification. So likewise for other points it is clubbed. So the input classes are clubbed in a manner to maintain equal frequency in the output classes, and that is the outcome here. So this will have a better uniform representation of each class in the output as compared to equal interval classification. Okay, and so that was about classification. Now I would talk about measurement operations which can be performed on raster as well as vectors. On rasters they are much easy, because the raster structure itself makes it easy. You just have to know the pixel size, and you can calculate the other measurements by just multiplying the number of pixels with the pixel size. And in vectors the calculation is little intricate, and it requires algorithms to be written. So it is little more complicated as compared to raster. So here I show you for the calculations for point, line and polygon. If you have 2 points, if you have a point map, you can calculate simply the number of points, their closeness. You can express that in terms of some kind of index, point index or point pattern index, nearest neighbor index. When you have line features, you can calculate the distances between the 2 points. So this is just the distance between 2 points. You can calculate that as a length of the line, and you can have minimal length as well as the maximum length various lengths are possible here. When you have two data points, you want to find out the distance between them. You can have minimum distance, you can have maximum distance. For a polygon feature, you can have a bounding box, you can have perimeter, you can have area, you can have centroid location, and how much boundary is shared between two polygons. Lot of measurements are possible on polygon itself. So individual features we can have, feature types, we can have measurement operations, and we can also have measurement operations in between feature types. So between point and line, between line and polygon, between point and polygon. In case of rasters, the measurements are very easy. You just count the number of pixels and multiply it by the cell size, you get the area. So you can find out the location. Location addressing is very easy because you know that it is a row and column addressing. So just by knowing the row and column value of each pixel, you can know the location. Distances, I said, you can use the Pythagoras theorem, or for the diagonal cells, the straight distances work for the the orthogonal cells, and area is calculated by in this manner. The distances can Pythagoras can be used for that. So that is how you make calculations on rasters for making measurements. Now I talk about overlay operations. Just two rules I want to inform you before we can further proceed for the type of overlay operations. So standard overlay operations take two input data layers at a time, and they assume that they are georeferenced in the same system. The coordinate system that is used and the datum, everything is the same. And the other assumption is that there is an overlap in the study area. If you have an study area like this, for example, this is Dehradun district, there is Haridwar district, there is no overlap between the two, then we cannot perform overlay operations on these two layers. So these two conditions have to be met in order to perform overlay operations. If either of these conditions is not met, it is not sensible to perform overlay operations. Why do we do overlay? The purpose is to compare the characteristics of the data set based upon these data layers, and to produce a new output which has got some additional value. Okay, so here I will show you. So these are there are various possibilities in raster and vector. Usually whatever you can do in vector, you can do in raster, and vice versa, but with some differences. The way of doing things changes little bit. So in case of vector, you have these topological overlays, like for points, lines and polygons. You have different operations. For rasters you have different, like you have intersection, clip and overwrite. I will give you an overview of all these. And in case of rasters, you have this I already talked about, the arithmetic, logical, conditional operators, and you also have other functions I will talk about. So in case of raster overlay, the new cell values are calculated using the calculus. It is basically you can find out in a software using the raster calculator or the map algebra kind of operations you can look for. There are various kinds of raster functions: local, focal, zonal and global. The local functions are performed on cell by cell basis. There is geometric calculations are not required, as I said. They are very easy rather to trace the geometric calculations. You don't need to calculate the other distance. You just have the cell size and the row and column addressing and the number of pixels in each representing each feature. That is more than enough. You don't require the other calculations. The expression looks like something like this. I will give you an example of these. Like for example, you have a map A, map B. To calculate map C, you can have just a simple operator, map A plus 10. So that is a kind of exaggeration, as we talked about in my initial class also. There we used multiplication as the operator. Here it is addition. But the effect is little less than the multiplication, but it is also a kind of exaggeration. So because you have more added by 10, so each cell value is added by 10 here. So it is a local function. Now same is for map C1, but map C1, instead of adding a constant, we are adding another map. So the dimension, this is, please note that this is not any matrix addition, this is a simple cell by cell addition. Similarly, this multiplication is also not matrix multiplication, it is only cell by cell multiplication. Division, multiplication, addition, whatever it is on cell by cell basis. So this is a very useful index. If you use it on images, it is called NDVI index. If you use map A as the nearest, as the infrared band, and map B as the red band, then you get the NDVI, the normalized difference vegetation index, represented by C2. So these simple addition and subtraction can lead to lot of good useful statistics which can do value addition to your data set. Now you have relational overlays, like using the relational operators. Here is a comparison statement, output is equal to map A greater than map B. So if this statement is true, then you will get a 1, else you will get a 0. So here map A is 5, map B is 4, and map A is greater than map B. This condition is true here, so you get a 1. But wherever it is not true, like this is 2, this is 8, so this condition is false, so you get a 0. You get a Boolean output as an outcome of these relational and conditional operations, and this is a Boolean output. You can also have include fuzziness in nature by having some more data values. You will have to have a layer of values in that case. Now this is an example that I also showed in my previous class. So this is AND statement, the logical AND operation performed on vector data set, and this is how it shows where are the forests which are steep in slope. So steep forest areas are highlighted by the green color here. Here you had no data, so it resulted in no data, and rest of the places are false. So the gray is false, the green is true, and this is no data. Now I will talk about the vector overlay operations. They are named after the Bonham Carter, the two mathematicians who had proposed these. So here there is a general principle for each of the operation, and then I will talk about what are the differences between various operations. So here you see that you have map A and map B. Map A has got, let us say, two polygons having these attributes in their tables, and same is for map B. When you perform the overlay, unlike the retrieval, selection and measurement operations where there is no topology built, no new intersection takes place, no new feature is created, in case of overlay operations, all of this happens. That is, the topology has to be built because the intersection takes place, and this causes the new features to be created, and therefore topology has to be built again. So this is a general principle, and all the attributes or maybe some of the attributes of the two maps are copied to the output. So that is a generic statement, but this will vary from type of operation to one operation to another operation based upon what type of operation it is. So there are two categories usually. There are spatial join operations and feature extraction operations. In case of spatial join operations, which are identity, intersect and union, the features from both the data layers are merged to give to create a new layer. The main difference among them is the way these special features are selected for processing, but in the attribute table the same rule applies. That is, the attributes from both the maps are copied. Okay, in case of feature extraction operations, the features from the operation layer are not copied, only the attributes from the original layer are copied, but the spatial extent is chosen from the operation layer. I will show you how it works. I will show you an example. So here if you look at intersect, let me show you the figure. So if this is map A and this is the input map and this is the intersect map, we call it as operation layer. Then this is how intersection works. So this is the input and this is the intersection. This is a kind of mutually exclusive operation wherein even if you exchange any of this, so for example you make this as input and this is intersect, the output will not change because only the common area of both is taken. The corners of this rectangle are not present. Similarly, the some part of the circle is not present here, like this one and this one is wiped out because this is uncommon area. This is not common to both the maps, but the attributes that are copied are from both the layers. Okay, 1 2 3 4 as well as A and B. So both are thing, and you see the new ident are given to each polygon which is created, because now there are 8 polygons out of these 2 and 4 polygons. So now there are 8 polygons. They will have attributes from both of these maps. So that is the intersect operation. Only the features inside the common area of the two input data sets are kept in the output. The one data input data can be point, line or polygon, but the other has to be a polygon. That is a condition. Otherwise you will not be able to perform intersect operation. So the output looks like this. Input attribute 1 and input the other input attribute both are copied to the output with the new polygon IDs built created. So the new topology is created. This is the same thing. Now overlay, this is actually a clip operation. This is the input map and this is the clip map or the operation map, which is since we are doing clip operation, it is a clip map. So when you perform this clip operation, it is like a cookies cutter. You know, you take a bigger thing and you use a cookies cutter to cut the entire thing into smaller pieces. So this is, it can be small or large, that is not the point. The point is that this out boundary of the clip operation, sorry, of the clip layer decides the output, the the extent of the output. So the attributes or the features are copied from the original layer, that is the input layer, but inside the boundary of the clip layer. It is like a masking or cookies cutter operation. Okay, restricts the spatial extent to the outer boundary of the clip layer. No other polygons from the second layer play any role. It is only the boundary of this is used for cutting. So that is the clip operation. It is a feature extraction operation. That's why no attributes from this layer will be copied to the output. There is another operation called override by. So you have instead of doing the clipping, now the attributes of this layer, the override layer, are copied to the output. All the attributes to this, but wherever this is used, this is very useful operation for performing the updating the data set. Suppose you had a road layer, you want to update your road layer, you want to replace the old road which is not present now, but a new road is created. So this kind of operation will be very useful. And you also have I'll also discuss these operations. Let me go back to this slide. Yeah, the identity operation and the union operation. The union takes into consideration all the attributes as well as special features of both the layers. So unlike the intersect, it is actually reverse of intersect. It takes it makes a union of both the special features as well as the attributes of both the layers. In case of identity, it is similar to clip operation, but it is little different in the sense that, or maybe you can say it is similar to union and intersection, but the extent of the input layer is preserved. The extent of only that portion of the overlay or the identity layer is copied, which is inside the input layer. This is used for let's say you are working on a study area. You have the roads from one data source. Now you also got roads from another data source which cover other areas, but which have got some updated roads for your data set. So you can overlay that and you can get the identity. So all, or maybe you can a better use will be, you have the road map, and you have a administrative boundary map, let us say. So each ward is represented in the other identity layer. So you want to get the identity of each word on each road. So you perform an identity operation. Your input primary boundary, primary layer boundary will be preserved. All the features inside the primary layer will be preserved, but the identity of the word will be used, will be assigned to each road in your primary layer. So for assigning the identity of another attribute, another layer, we use identity operation. Similarly, here in the feature extraction operations, the erase command is used as a reverse of clip command. We have to erase some area. For some reason, we want to erase out the features, and we want to be left with only the remaining area. We use erase operation. I have one example where, if time permits, I will show you that. And then reselection, selection I had already shown, so I will not go into detail of this. We have already seen enough examples of the selection commands. So this we already discussed. Now let us discuss the raster functions, the local, focal, zonal and global operations. I'll discuss each one of them on one by one. I just wish to tell you that anything that you can do on raster can be categorized into one of these operations: local, focal, zonal and global. And this applies for not only on maps but also on images. Anything you are doing with raster structure can be classified into these 4 categories. So what are these? Let us discuss, and then I'll show you some examples of them. So local functions are the ones that work on cell by cell basis. I showed you already some examples like this NDVI, or even this NDVI is an example from image processing, but similar thing you can do on the maps as well. So map A plus 10, map A plus map B, map A minus map B, all of these are performed on cell by cell basis. So they are local functions. When you perform focal functions, what happens? That you imagine a foci of points. This foci can be called as foci, or focal, or window, or kernel, or neighborhood. So basically you are considering the neighborhood of location into consideration to make calculations. That is the idea. And it processes the data of each cell based upon this foci or this window or this specified neighborhood, which could be square, which could be rectangular, it could be circular. So you could define the shape and the size of this kernel or this neighborhood, and based upon that you will perform the operation. So the central value, cell value, will be replaced by considering the values in this neighborhood. That is the idea. And then zonal functions consider a particular zone grid. So that zone grid will be used to perform the operation, and all the operations will be performed zone wise. Okay, and in case of global functions, they consider the entire grid into consideration to make the calculations. Right. So let us see each one of them with examples. So here let us say we have a grid and I wish to multiply it by value 3. Please notice that there are no data cells also, which means there is no data available for these cells. So when I perform any operation, the no data cells here will remain as no data cells. And when I perform multiplication by value 3, each cell value is multiplied by a value 3. So you see, 2 into 3 is 6, 0 into 3 is 0, like that. So this is a cell by cell multiplication. You can also perform cell by cell division, multiplication, addition and other operations. Even trigonometric operations you can perform. You can also multiply it by another grid instead of multiplying with by a constant. So here please note that this is not matrix multiplication, it is a cell by cell multiplication. So there has to be there is a assumption that you have to have equal number of cell values in each of these grids that are being multiplied or divided or whatever operation you are performing. So here we say 2 into 1 is 2, like that you are performing the local function. You can also perform trigonometric, geometric, other calculations, logical operations. We have already seen usefulness and examples of these in previous slides. Then focal functions are performed on based upon a foci of points. So imagine a foci of points that is let us say here. If I want to make the modification in this cell value, I am considering the neighborhood of 3 by 3. So if I say performs focal sum, what I need to do? I need to imagine a window of 3 by 3. Within this 3 by 3 window, I add all these values and replace the central value by that value. That is why it is called as focal sum, the sum of all the points in the foci of points. So that is 4 plus 4 plus 4 plus 4, that is 16. So you get similarly other cell values are calculated. So a focal sum function sums the values of the specified neighborhood to produce the output grid. Instead of focal sum, you can calculate focal mean, focal standard deviation, focal maximum, focal minimum, and this slide shows how focal mean is calculated. So you can perform a focal operation and then a local operation of dividing each cell by a value 9 to get the focal mean. You can also directly do in the one go itself. So you can say 16, here itself you could say 16 divided by the number of pixels, that is 9. The 9 is the number of pixels in each focal or the neighborhood, that's why you are dividing it by a value 9. Please note that at the edges this foci of points reduces to 2 by 2. You also have other alternates of adding some artificial values here and here at the boundaries, or you can simply divide it, you can reduce the size of the neighborhood to 2 by 2. So for this cell, as the center cell, you have these value will be considered. That is why you have the sum as 7 and 7. I think there is something wrong here. Okay, it's not wrong actually, because this is 7 and the number of cells in the neighborhood is only 4, so that's why 7 by 4 is 1.8. So because the cell number of cells in the neighborhood has been reduced to 2, so accordingly this is being calculated. So this is a focal mean. Likewise, you can calculate the focal standard deviation, focal maximum, focal minimum. Now you would be wondering why would we use the focal function. So these functions are used for smoothing of the data, for highlighting some specific differences. They are very much used in image processing as filtering operations. So the way local functions are useful, we also have utility of these focal functions. And then the third type is the zonal functions. Here each zone is considered for doing the processing. So I'll first give you an example. Like suppose you want to make valuation of each land use type. So you will use the land use line cover map as the zone grid and individual cell values as the value grid. So let us say this is your input zone definition and this is your values that are telling the value of each cell. So if you want to perform a zonal maximum, you will consider each zone and try to find out what is the maximum value inside this zone. That value you will assign to the output to that particular zone. So for example, let us take zone 3 as an example. This is the definition of zone. This is zone 3. The maximum value here is 7. So the entire zone 3 is now replaced by a value expressing here the 3 is not the value, it is the definition of the zone. It is zone 3. But here, because we are taking the value from the value grid, this is representing the maximum value inside this zone. So it is a zonal maximum operation. So this is, you can also think of its utility, like you want to know which is the city or which is the ward which is having highest elevations. So you will perform a zonal maximum and you can tell that this is the zone, this is the ward that has got maximum elevation. Highest elevation values are present in this zone or this ward. So you can perform a zonal operation. So to explain you that they process the data of a grid on a zone by zone basis. A zone consists of number of cells that may or may not be contiguous. So here in this case you see the zone 2 is not contiguous. Even zone 1 is not contiguous. They could be having some breaks as well. They are still, for example, forest. Forest need not be present only at one place. It can be here, here and here. So you can have non-contiguous polygons for defining the zone. In the zone grid, cells of the same zone are coded with the same value, while the zones are assigned different zone values. So you have different zone values here. The different names are assigned to each zone, and within that the value may be same or different. Like in this case, like in this zone, the value grid has got a value 2. The first zone also has got a value 2. So value may be same or different, but the zone definition is different. It is non-overlapping. No two zones can overlap as such. Okay. So that is a zonal function. And now finally, let us talk about the global functions. So I'll take you to the example and then we'll come back to this slide. So let us say, we are, let's say, administrator, and who want to, there is some emergency situation and we want to have, let's say, 2 fire stations are there. We want to tell, maybe there is some, fire in the area. Because we know that there are 2 fire stations, we want to divide the area into 2 fire stations. Or you could even think of a hospital. There is some accident and we want to take the people to the nearest hospital. So let us say there are 2 hospitals here, and we want to know which cell, which area will be nearest to this hospital. So to do that, we need to consider both the facility points, the 2 hospitals, and all the cells. So this is performed on entire grid at the same time. So for example, let us consider this particular cell. If I assume that the cost of traveling any cell is unity, it is the same, then cost of traveling from here to here will be, from this is calculated from center to edge and edge to center. So from here to here it will be 1, half and half, that is 1. From here to here it will be, from here to here it is 1, but from here to here it will be, if we use Pythagoras theorem, it becomes 1.4. So this is the nearest cell, and that is why we assign the Euclidean distance to the nearest source. So we assign a value 1.0, not 1.4. You see here 1.4. Similarly for this one, the 1.4 is the nearest distance because this will become higher. So 1.4 is assigned here. Likewise, you keep on assigning the value or the distance that is to the nearest source. That is why you get these values from ranging from 0 to 2. You could also, if we have a bigger grid, then we could also have values like 3 and 4. But since we have only 4 by 4 grid, the values are ranging up to 2. This is assuming the unity cost of travel. But suppose instead of unity you had some value grid, some cost grid, which means the cost of traveling each cell was not uniform. Then this value grid or the cost grid has to be considered in order to calculate the distances. So the same value which was 1.0 has now become 2.5 because there is a cost grid 2 here. So since this was the nearest source, if you calculate it this way, so cost of traveling from center to edge will be 2, and from this, because it is unity cost, from here to here it will be 0.5. So that is why this becomes 2.5. If you consider like this, then again an additional cost of this and this will be there. That's why this is not nearest source. This is the nearest source, and the cost of traveling this nearest source is 2.5. That is the distance. The distance to travel this nearest source considering the cost grid is 2.5. That is how we make calculations globally. That is, global functions are calculated. You could also have cost path function which identifies the least cost path for traveling from point A to point B. So this has got applications in many useful utility applications, and also in network analysis and connectivity operations. The global functions are used. Also in landscape and analysis also they are used. So these are the global functions. So that was about raster functions. Now I will talk quickly about the neighborhood and connectivity operations. So there are various methods to do proximity calculation using buffer generation and Thiessen polygons. So Thiessen polygon is based upon an algorithm called Delaunay triangulation, which divides the data into in a specific manner using the Delaunay criteria. And then there are seek and spread kind of functions. So I'll quickly show you the buffer zone, but But the basic idea about the neighborhood operations is like this, that you are concerned about your neighborhood because your neighborhood influences you. So in this case, if you want to consider, for example, you want to know what is the air pollution, or where the air pollution will spread if the polluting industry is here. So you can make a buffer zone. If you know that 2 kilometer distance, up to 2 kilometer distance is not good, you want to erase this, so you will find out a buffer zone of 2 kilometers from this place which is polluting. So the station which is causing the pollution. So you can have this kind of a buffer zone, consideration of neighborhood. You can also have a constrained straight line, considering the road network into picture. You will have the straight line kind of distances as well. So you can have both ways, aerial distances and straight line, or the road distances. So that will have a different shape and size of the buffer. But usually buffer is an aerial expansion of features, whether it is a point, line or polygon feature. As an input, the output will always be a polygon feature. So these are some examples of where, in what situations you will have influence of neighborhood. How many people live in the area? I want to buy a land. How many people live? What kind of people live? What is their average income? So all these things we may like to consider. In case of buying a land or house in an area. So are there any high risk industries? How much distance I am at, my plot or my house is at from these high risk industries. So like that, for this kind of purposes you may have to create a buffer zone generation you may have to do. So buffer can be of two types. It could be a fixed width buffer or it could be a variable width buffer. Here we show you that for different categories of roads you can have different width of buffer. So for example, for highways you may like to have a bigger buffer. For the streets you may have to have a smaller buffer to know what is the width, or to have a automatic calculation of the widths. So we will use the variable width buffer here. As I said, it is an aerial expansion of features. It does not take into account the direction, it calculates in both. But you can specify the left or right, whether you want to generate the buffer towards left or towards right. You want to have round corners or flat corners, you want to dissolve the features or you don't want to dissolve the features. So those kind of specifications you can give while generating these buffers. It actually depends upon how that program has been written. Okay. And this is a multiple ring buffer, wherein same width has been used but not one time but multiple times. So this is a multiple ring buffer on the same set of roads, same set of features. So 1, 2, in this case 2 rings are used, but you can have more rings as well. So this may be your primary area of interest, this may be your secondary area of interest. For that you may have to create multiple ring buffer. So between 0 to 100, between 100 to 200, 200 to 300, the last one, this one is, sorry, 3 rings, the last one is colored as white. Okay. Then connectivity operations are used in heavily in network analysis, and they are also used for location allocation kind of problems, for tracing the faults in a network, for optimum path finding, whether it is ordered or unordered path. I will talk about these, what they are. So we can have planar and non-planar networks. Like planar networks will follow only one level of so embedded in two-dimensional plane, like the water. But if we have a canal as a as an additional, so we can have non-planar as well. Like in case of road, we can have underpasses and overpasses. So that is a non-planar network. Multi-level crossings, underpasses, overpasses will indicate a non-planar network. While the natural water is a, but if we create an artificial water system, then it may also be a non-planar network, right? And what kind of analysis we can perform on networks? We can perform optimal path finding, network partitioning. These are the two basic categories. So optimal path finding is generating least cost path on a network between a pair of predefined locations. So I have points A and B, and I want to find what is the optimum path to reach this point from A to B in the fastest manner. I could take this criteria of fast as time or distance, or maybe even scenic beauty if I'm a tourist. So I can even take some other parameters, but usually we define the impedance in terms of distance or time. So this distance, this impedance basically constrains the path finding. The operation is similar to the Euclidean distance finding in the global function that I explained. But if you put a constraint, then you have to, it is something like considering a cost grid. Okay, so network partitioning assigns the elements into one zone or other zone. So even in that global function I explained, if you have to allocate an area or a fire station or a hospital to an area, so you can use the Euclidean distance function or maybe some other functions to do the partitioning. Then trace analysis can also be done. I'll show you examples of these. So optimal path finding, as I said, is from origin to destination. What is the path? What is the optimum cost path? So considering the impedance and the origin station, the final destination, and the length of the segment, you can make calculations and you can find out this optimum path based upon certain algorithms. I'll not discuss those algorithms in detail other than the distance that I already discussed with you. I'm sorry, my no, throat is not so well today. So ordered and unordered path can be found. I'll give you an example. Like suppose you have a pizza delivery boy. So you know the condition that it has to deliver pizza in the given time, let us say 30 minutes. So those who ordered first have to get the delivery of the order first. So it does not matter whether it is near or it is far, the order of the the sequence of the order given is important. So accordingly it will be an ordered path. But if suppose a postman has to deliver letters, he has to deliver in a day, but there is no constraint whom have to be delivered, who has to be delivered first or last or second. So in that case we can follow the unordered path and we can try to optimize the the cost of travel or the time of travel. So we will take, like in this case, this is an ordered path wherein you have to travel more. A pizza delivery boy has to travel more because he has to fulfill the condition of the time. Here in this case you may not appreciate that because he could still deliver. If suppose these distances were less, then he could still deliver up to 2 points in that same time. But if suppose imagine that these distances are very large, then he has to follow this unordered path, this ordered path, that he has to first go to first and then to second, then third, and then fourth. But in case of postman, he may go like this, optimize the path. So you can see that the distance traveled is less as compared to the ordered path. Okay, I hope that is clear. And partitioning, as I said, it could be partitioning based upon simply the distance, or it could be based upon the constraint based upon the travel, like travel on the road. So this is aerial, this is a constrained allocation of the facility. Usually when you do the location allocation, you have more points like this and you have to decide which, for example in this case, which areas to be allocated to this facility, as I showed in that global function. So in this case the road is considered here to constrain this the allocation. So that is why you can see a reduction, because there is no road here, so you can see that there is a reduction here. Okay, so this is a network partitioning which can be done using network analysis. And then finally the trace command, which is like a conditionally connected network. So if you want to know, let us say there is a leakage in the supply of some goods, maybe water or electricity, and you want to find out the fault. So how you trace that fault? That is why the name to the command given is trace, because what you will do is you will consider each node at which it is connected, these sublinks are connected, and you will try to find out. Now if I disconnect this, conditionally disconnect upper portion or the lower portion, where is the leakage, whether we are getting the current or not, or maybe water. So you make conditional connections, and you try to analyze the network in terms of input and output, and accordingly you can try to trace the where the leakage is, the leakage point you can trace with the help of trace command. All of these commands are implemented in most of the GIS software to find this conditional connection. There are other commands like Thiessen polygon, which is based upon Delaunay triangulation. As we are already running out of time, so I'll just quickly show you a few more things. I just want to show you analysis. We already discussed these steps, but I want to show you an example with these steps, and then I would like to conclude. So here let me show you an example of. So I had told you that you first need to specify purpose, and then decide the criteria to perform that, to meet that purpose, and then you have to execute in certain manner. I had also given you the steps to perform spatial analysis. So let us say that our objective is to log trees from forest, okay, and to be profitable I want to log a specific trees, in this case ponderosa pine. Now when I do logging, the environment will get negatively affected. We don't want that to happen, so we will put some criteria so that we can make an environmental savvy choice of the sites where we should log. So let us say I give the criteria of soil quality and then steep slopes, and also wildlife habitat. So what I say that to avoid soil erosion, because when you log, the good quality soil goes into gets affected, and soil erosion takes place. So also the water quality goes down, because the good quality soil goes into water, especially if you log from the steepy slopes. So we will say that to avoid soil erosion, we will not log the trees from more than 20-degree slope. And same thing we will say for water quality, that areas within, let us say, some specific distance, here in this case we are telling 400 meters of wetlands, would not be logged. In this case 20-degree could be changed to 18 or 15 depending upon what the experts suggest, or we can have a look at the values in our study area and decide. But to apply this criteria of sensitive wildlife habitat, we will simply say that avoid the areas which are habitation of some sensitive wildlife that is residing there. So let us say, with these three criteria plus one, this ponderosa pine criteria, we have to perform a site suitability analysis. So how we will go? We will prepare the, first of all we will identify what we require. So to get the ponderosa pine, we require a map, vegetation map, and we need to make certain selection. So selection by attribute we can make to get the ponderosa pine. Let us say this is my ponderosa pine locations, and there are other vegetations, but I have highlighted here only ponderosa pine. And then to perform this second criteria, the operations based upon the second criteria, I need to classify my slope into 20-degree slope and less than or equal to 20-degree. So let us say I have done that, and I have also got this sensitive wildlife habitat map from, let's say, the wildlife organization which is having this kind of information, and these areas have to be simply removed. So I perform, and for the water I make a buffer of 400 meters around the water bodies. All of these preparations I do, and then carry out integrated modeling using the overlay operations or either of these raster operations. So let us say we are performing a vector overlay, and this is how the physical overlay looks like, but a logical overlay will be slightly different. As you can notice that we have to remove the steepy slopes, the sensitive habitat zones, and also the buffered water features. So what will remain finally will be the visible green portions, which will be the suitable sites based upon these given criterias. Now these criterias we can further refine and try to refine our analysis. But if we don't do, then these are the sites that are suitable sites. We can further refine them, by applying certain area criteria, or the polygons that are smaller we will not do, so we can remove. Okay, so that is how we can perform spatial analysis, the site suitability analysis in GIS. To do this kind of operation, we can simply use one command, that is erase command. Now we have to do just one attribute query to select each of these, maybe few classifications and one buffer zone operation, one classification for classifying the slope, and then erase command. So these four commands will do the entire analysis. You can also find out other ways to do this analysis. There are many ways to approach the same problem, so you can use different operations as well. Okay, you can use union and then reselection, or you can use a union plus intersection also could be used here. So you can think more ways, and maybe you can report back to me what did you use in this kind of analysis. I think with that I would like to end my lecture. I would like to tell you that you should formulate the criteria depending upon the aim and objective of analysis. You must understand the data in totality. It is very important to deal with the errors that are present and to maintain the data quality, and selecting the right parameters for integration. With this, I wish to thank you. I had jumped here to these, and let me concluding slide.